Greetings grade 11s and grade 12s, and welcome to Ubuntu Academy, lessons that empower. We are back again with Newton's laws and applications of Newton's laws. Today we are looking at lesson 3, where we are going to be looking at the components of weight. In other words, we are looking at the components of the force of gravity, how to draw them on a free body diagram, and also how to calculate them when we are given the mass of an object which is placed on top of an inclined surface. In other words, that a surface that is not vertical or horizontal. Okay, now before we go straight into such a situation, we need to recap on a little bit on a section that we did under the topic vectors in 2 dimensions. There was a section that we did that is called the resolving of a vector into its components. Now in this case, we are going to be looking at force F that is acting at an angle. As you can see on your screen, there's a force F there that is acting at an angle theta. Okay, now when you have a force like that one, the force, as you can see, is not parallel to the surface, neither is it perpendicular to the surface. What we learned from the topic on vectors in 2 dimensions is that you cannot work with a force when it's like that. It has to be resolved into its components. One component must either be perpendicular to the slope, perpendicular to the surface, or parallel to the surface. So we resolve this vector into its components. Okay, the first vector that we look at is what we call the horizontal component. As you can see here, this would be your horizontal component, right? It's acting in the x dimension. And then we also have Fy, which is what we call the vertical component, right? So we resolve this vector F into 2 forces or vectors, Fy and Fx. Okay, so you'd remember here we are going to use a little bit of trigonometry, but also remember that we have the method called the head to tail method, or the tail to head method, where we draw the second vector. This vector Fy is drawn starting from the head of the previous vector. The previous vector in this case would have been this one, which is Fx. Okay, this is the tail to head method. But we also have what we call the parallelogram method, which is the tail to tail method, where all the vectors are drawn from the same origin and where all the tails of the vectors are drawn from the origin. In this case, you would be drawing both the Fx or from the origin and also Fy. So this blue vector that you see this side is the same as that one. This is the same Fy. As you can see, it's still pointing in the same direction. It still has the same magnitude. So you can draw this vector either here or you can draw it there. It's up to you which method you are using. And it's also important to remember that when we look at the objects that are placed on top of a surface that is not parallel or perpendicular to the lines of your book, because you in some cases will have to move one vector and draw it from the tail instead of from the head. Okay, so the calculation, now comes the calculation part. We have to start by the horizontal component. The horizontal component, like we did say, is the Fx. That's the horizontal component. But before we move there, I want us to focus on this triangle here. Okay, let's assume this would be your triangle, let's say triangle ABC. So I want you to focus on triangle ABC. All right, just remember that. Now if you're focusing on this triangle ABC, you would realize that this is the side that is adjacent to this angle. Okay, so that is your adjacent side, and this side is the side that is facing the angle, and the side that is facing the angle is referred to as the opposite side. Okay, we need to remember that when we do the trigonometric part. Okay, the part that is facing this side is facing the right angle. Therefore, that is what we refer to as the hypotenuse side in trigonometry. So we have 3 sides of the triangle: the adjacent side, the opposite side, and the hypotenuse side. Okay, so if we want to calculate Fx, we do realize that Fx is going to be related to cos theta, and the reason for that is because we have the adjacent side here. The adjacent side, if you say cos theta, is going to be equals to Fx, which is the adjacent side, over the hypotenuse side, which is F. Okay, we know cos is adjacent over hypotenuse. The adjacent side in this case is Fx, and the hypotenuse side is equals to to f in this case, okay? But we want to calculate fx as we indicated here. Because we want to calculate fx, we can make fx the subject of the formula by multiplying, by multiplying this side by f and also multiplying that side by f. If you do that, now what happens is that let me just remove this disturbance here. What happens is that this f will cancel that f over there, and what you're going to be left with now is f times cos theta, which is this f times cos theta there is equals to fx, right? Now in the next part then we write fx on the left hand side. We say fx is equals to f times cos theta, and that is how we get the formula for the calculation of fx. So fx is calculated using the formula fx is equals to f multiplied by cos theta, and that is how we get to that formula by using simple trigonometric functions. Okay, we move now to, we're going to use the same method, but now we're calculating fy. So if we're going to use trigonometric functions for fy, which is going to be our vertical component, that would be sine theta. The trigonometric function that will work there is going to be sine theta. Okay, sine is equals to opposite over hypotenuse. As we can see, opposite is fy, hypotenuse is still f. So sine theta is equals to fy over f. Again, because we want fy, you can multiply both sides by f. Okay, if you multiply both sides by f, this f will cancel that f. What you're going to be left with is that f multiplied by sine theta is equals to fy. Okay, and then we make fy the subject by putting it on the left, and we get the formula fy is equals to f multiplied by sine theta. I need you to remember the skill that we applied here. Don't memorize, just make sure that you understand what we did here. A simple trigonometric functions where we use cos as adjacent over hypotenuse and sine as opposite over hypotenuse. Okay, that's how we get the formula for calculating the x component of a force acting at an angle and the vertical component, which is fy acting of a force acting at an angle. Now let's move to what we prepared this lesson for. Now we're looking at objects that are placed on an inclined surface. Okay, so when an object is on an inclined surface, the weight, remember what the weight is, we did this in the first lesson. The weight is the force of gravity. In this case, the force of gravity does not act parallel nor perpendicular to the surface. You'd have seen this before, but we're going to look at this again in an example below. So the weight always acts perpendicular to the horizontal line. Remember when we did the lesson on free body diagrams, that was lesson 2. We kept on emphasizing the fact that the weight or the force of gravity must always act perpendicular to the lines on your book, and those are the horizontal lines, regardless of how the slope is. We even did an example of this on the strategies. Regardless of how the surface looks like, the weight or the force of gravity must always point towards the bottom of the book or perpendicular to the lines of your script. Okay, now for the purpose of calculation, this is purely for the purpose of calculation, the weight, which is what we refer to as the force of gravity, Fg, must be resolved into two components, the same way as we did in the previous slide. We need to resolve this weight or the force of gravity into its components. One component of that weight must be parallel to the surface or the slope, and the other component must be perpendicular to the slope. Okay, that's for the purpose of calculation, because we cannot use the weight if it's not parallel to the surface, neither is it perpendicular to the surface. So we have to resolve this weight into its two components, one of them perpendicular to the slope and the other one parallel to the slope. And how do we do it? Let's look at a scenario here. We have an object. As you can see, there's an object. It's placed on top of a surface which is at an angle, and this is what we call a slope. The surface is acting at an angle because it's not horizontal. Remember, this is the horizontal line. The one at the bottom is your horizontal line. Okay, as we can see, this one is our surface. Okay, excuse me, this one is the surface, or what we refer to as the as the slope. Just make sure that you understand the difference between the two. The one at the bottom, the one that is horizontal or parallel to the lines of your book, is the horizontal line, okay? And this one here is the surface where the object is placed. Our object is in contact with the surface, okay? Now, we know that if we need to draw the free body diagram, a normal free body diagram, we are going to draw the weight or FG as a line that is going to be perpendicular to the lines of the book or perpendicular to the horizontal or pointing towards the bottom of the book. As you can see, it's pointing towards the bottom of my script. That's how we draw the weight. But we cannot use this weight or this FG. As we can see, there's FG and there is the surface. Once again, the two are not parallel to each other, neither are they perpendicular to each other. So we need to resolve this FG into two components. One component must be perpendicular to the slope and the other one must be parallel to the slope so that we can be able to do normal calculations. And this becomes extremely important as you move forward, especially when we do the laws and the relationships between the forces according to the laws. Okay, firstly we are going to start with the perpendicular component. As you can see, there is the component of, this is the component of FG, but this is the component that is what? Perpendicular to the slope. Okay, so that we call it FG perpendicular. In other words, this is a component of FG, but it's the one that is perpendicular to the surface or the slope. The second one, if we use the head to tail or the head to tail method, yes, it's going to be drawn from the head of the previous vector, and that is your FG parallel. Why do we call it FG parallel? Is because it is parallel to the slope. As you can see, it's parallel to the slope over there. It's parallel to this slope. Okay, so that would be your FG parallel. But for the purpose of calculation and drawing of free body diagrams, we know that when we draw a free body diagram, all the forces, including this one, must be drawn starting from the object being the dot on top of the surface. So remember, when we use the parallelogram method, we can draw all the tails from the same origin. So I'm going to move this vector and draw it just to duplicate it. That's your FG parallel, but now it's drawn starting from the origin or the object that the forces are acting on. Okay, so just remember, this FG parallel is the same as that one. The reason why we have this one, this side, is because we are going to need the triangle to figure out how to calculate this FG parallel. This one is the one that you are going to, this type of drawing of FG parallel at the top there is the one that you are going to use a lot when you are dealing with the Newton's laws, when you start looking at the relationships. Okay, now let us look at this situation. We do have a triangle here with three sides. We have FG on one side, we have FG parallel on the other side, and we also have FG perpendicular on the other. So we do have the three sides of this particular triangle. Now we need to figure out, like we did in the previous slide, how do we find a way to calculate FG perpendicular? How do we find a way to calculate FG parallel? The most important thing that we need to get from now, and I get this a lot from learners asking the angle here that we are using. We are going to use this angle. There's a reason why in your examination they give you this angle, because that angle actually is the angle that is the same as that angle there. Okay, so this theta here is the same as that theta over there. And just for the purpose of to benefit those who are curious as to how do we get that, just let's do a little bit of mathematics. I'm sure we can all agree, okay, just for to benefit those who really want to know why do we put theta over there. We will all agree that this is the same force. Okay, these two lines are parallel to each other. This line is parallel to that line. Okay, now having said that, that means the angle here, let me just quickly change the color again. Maybe let me use black. This angle here and this angle here are the same because these are alternating angles. Okay, let me just remove this. These two angles, because this line is parallel to that line, these two angles here are the same. Now I'm going to call this angle here angle X. Okay, and this angle also angle X, right? Now what do we know? We know that the three angles inside a triangle must give us 180. Okay, which means theta plus 90 degrees, because the angle here is going to be 90, plus x must give us 180 degrees. Okay, now if we want theta, you'll then realize that actually theta is equals to 90 minus x. If you solve that over there, because this you transpose that 90 and the x to the other side, you're going to find that theta is equals to 90 minus x. Okay, I want you to remember that this theta here is equals to 90 minus x. The reason is because these two angles, theta plus x, must give us 90, so that when they combine with the 90 over here, they must give us 180. Now that is if you're focusing on this triangle. Now if you move to the second triangle, which is the one that we are working with, let me just clear all of this. Now we still have an angle here. Let's just call it angle beta. Okay, if you look at that, angle beta is also equals to, beta is equals to 90 minus x, which is the same as theta. Theta is also equals to 90 minus x, because there was x here as well. I just removed it by mistake. Okay, so this angle here, theta, is equals to 90 minus x. That angle beta over there is also equals to 90 minus x. Therefore, the angle theta is equals to angle beta. As you can see, angle beta is the one that we're going to be using, which is the same as theta. So that's a question that I get a lot when learners really want to understand why are we using that theta over there, although it's not part of the triangle. There is a mathematical relationship between those angles, and therefore the theta that we get, the theta that you are given as the angle between the slope and the horizontal line, is the theta that you are going to use for the calculation of the components of the weight. That will be your FG parallel together with your FG perpendicular together with your FG parallel. All right, now let's use, now that we know that this angle here is the same as that angle there, it's theta. Now let's use that information. Okay, we are going to start with FG parallel. Okay, now if we move to FG parallel, the parallel component of the weight, the parallel component of the weight is this one that is acting down the slope. It's always going to act down the slope, this parallel component. How do we calculate it? Now we have a knowledge of trigonometric functions, and we also know that angle over there is theta, is the same as the angle between the surface and the horizontal line. So we can use sine theta, because as you can see, if you look close, you'll see that this side is actually the opposite side, because it's the one that is facing the angle. Okay, and this one here, FG, which is your weight, it's actually facing the 90-degree angle, and therefore that will be your hypotenuse side. So this would be your hypotenuse side. I'll remove that just to make sure that it's still clear. Okay, so sine theta is always going to be equals to opposite over hypotenuse. The opposite side is FG parallel. There it is. The hypotenuse side, like we did indicate, is equals to FG. Okay, so sine theta is equals to FG parallel divided by FG, which is the weight, or you can just write W there. But because the reason why we have this, we want to calculate FG parallel. So in this case, we will then say multiply this side by FG and multiply that side by FG. If you do that, now this FG will cancel that FG. What are we now left with? We are now going to be left with FG parallel is equals to FG multiplied by sine theta, because as you can see, you are going to be left with FG this side is equals to FG sine theta. Okay, but remember, FG, there's a method of there's a formula to calculate FG. Remember, Fg is equals to the mass multiplied by gravitational acceleration, which is 9,8. We did that on the first lesson, lesson 1. On lesson 1, we did the calculation of weight. Remember, Fg is the weight. The weight is equals to the mass multiplied by the gravitational acceleration. If we then go and substitute this Fg onto this formula by replacing it with m multiplied by g, we get another formula, which is now the formula that we need to get used to, which says Fg is equals to mg sine theta. So that is the formula that we are going to use from now going forward. It doesn't change, it's always the same. it's always going to be there. Parallel component of the weight is equals to the mass of the object multiplied by 9,8, which is g, multiplied by sine theta. The theta must be the angle between the surface and the horizontal line. Okay, we are then going to apply the same method, but now to the perpendicular component, which is your FG perpendicular. Same thing happens here. If you look at FG perpendicular, you'll actually understand this is the adjacent side, because it's the line, is the side where the angle sits on. This one we did indicate is the opposite side. The FG is still your hypotenuse side. Okay, if we use the adjacent side together with the hypotenuse, we get cos theta, which is adjacent over hypotenuse, which is going to be FG parallel. We did say FG perpendicular is equals to the adjacent side divide by FG, which is the hypotenuse side. Of course, once again, if you multiply both sides by FG, if you multiply this by FG as well, this FG will cancel that FG, and what we are going to be left with is that FG perpendicular is equals to FG multiplied by cos theta. Again, remember, FG must be broken down into its formula, which is FG is equals to mg. Now mg can be then substituted into this, and then we get the formula FG perpendicular is equals to mg cos theta, and that's the formula that we are going to use from now on with regards to the calculation of the perpendicular component of the weight. All right, now in our worked example, we have a situation where a block of 12 kilogram is placed on an inclined or a rough inclined, as you can see, rough inclined surface that makes an angle of 35 degrees with the horizontal, as shown in the diagram above. The block slides down the slope. Okay, this is important, that is important, because as soon as you see rough, it means there is a frictional force, and because it's sliding, it means the object is moving, it's going down. This frictional force must be a kinetic friction, number one, because it's the box is moving, so it must experience a kinetic friction, and because it's moving down the slope, it means this frictional force must be up the slope. That is very important. Okay, now let's move to what the question is requesting of us. Now, draw a free body diagram showing all the forces acting on the block. Okay, usually the number of marks here are telling you how many forces to draw, usually, which is most of the time. Now, in this situation, we are expected therefore to draw 3 forces. Okay, now what are those forces? We know this is an object in contact with the surface, therefore there's going to be the normal force, and this is an object of a mass, therefore there must be a weight or a force of gravity, and because the surface that this object is in contact with is rough, it means there must be a frictional force as well. So those are the 3 forces that you need to draw on this particular free body diagram. Okay, we move straight into it. Now, the one thing that I actually advised you to do before you draw a free body diagram of an object that is on an incline, let me just change the color quickly of this thing. You need to make sure that this is not you're not compelled to do this. I did mention this even before, but I would really strongly advise that you do this. Draw first the surface, and do not put arrows on the surface. Here's the surface. Okay, now draw the free body diagram based on what you know about the forces in relation to the surface. I know that this object is going to be on the surface, and the first thing that I know about it is that it's going to experience a force of gravity, which is what we refer to as the weight. Okay, there is a force of gravity, or the weight. Now, the force of gravity does not, on an inclined surface, it's not going to be perpendicular to the surface, neither is it going to be parallel to the surface. We've already seen that in the previous slide. All right, it's going to be, the force of gravity is always pointing towards the bottom of the book. It's facing there, the bottom of your book, all the time. That's how you draw the weight. Okay, now importantly, now the normal force, our normal force, because this object is in contact with the surface, the normal force must always be perpendicular to the surface. So the normal force must be drawn in this direction. That would be your normal force there. Okay, Now the object is sliding down the slope, therefore it means the frictional force, the kinetic friction, must be up the slope, and that's what we call, and that's how, okay, let me just quickly put it this way. This will be our kinetic friction. The next thing that we need to do is to calculate the magnitude of the parallel component. Let me just put our labeling up there. And it's important, guys, to make sure that your free body diagram is labeled. Remember, the blue line is not part of the diagram. It's just there to guide us to draw the right normal force and the right frictional force, okay? It's not necessary for you to do it, but I'd really strongly advise, based on the number of mistakes that I've seen marking scripts of learners, that they draw the wrong free body diagram because they don't understand the relationship between the normal force and the frictional force together with the surface. Okay, now we are required to calculate the magnitude. In other words, then there's no need for us to deal with the direction here of the parallel component of this particular force. So if we are doing that, remember the parallel component is Fg parallel, and the formula for that is equals to mg sine theta. Please remember that just because the word says parallel does not mean we are using cos theta. That is used when you are resolving a force or a vector into its components. Here we are dealing with weight. When it comes to weight on top of an inclined surface and you are resolving the weight into its components, the parallel component, we use the trigonometric function sine, not cos, okay? And we see this a lot again with learners confusing the two, using cos theta for the parallel component and using sine theta for the horizontal component, and it becomes wrong, okay? Then we come to now to substitution. We know that the mass is equals to 12 kilogram. It's given to us there. Multiply by g is always going to be 9,8. Multiply by the sine. Again, I emphasize sine 35. Okay. Now we are then going to need a calculator to finish our. Now, if you use a calculator, then it becomes 12 times 9,8 times the sine of 35. Okay. And we get the answer 67,4525. So it's always advised that your final numerical answer must be rounded off to at least 2 decimal places. So we can just say 67,45 as our final answer here. Okay, so this would be 67,45 newtons. Of course, the force is going down the slope because this is Fg parallel, it's always down the slope, but because we are only required to calculate the magnitude, there's no need for us to write the direction. Okay, next question says calculate the perpendicular component. I hope you can see there because I've already written on top of the question there, but calculate the magnitude of the perpendicular component. What do we know about the perpendicular component is that perpendicular component is Fg perpendicular, which is always going to be equals to mg cos theta. Okay, when we substitute again, it's going to be 12 multiplied by 9,8 multiplied by the cos of 35, and then we get an answer there. Let's go back to our calculator and see whether we can what will be the answer here. Okay, now we have 12 times 9,8 times cos 35, and the answer there is 96,33 newtons. So the answer would be 96,33 newtons. Okay, it is perpendicular to the slope, as we did indicate before. Now, I know some of you are probably wondering now, but in our free body diagram, these forces are not there. That is because we did not draw the forces, we drew the vector that is responsible for those components. Okay, if you were to draw the free body diagram and include those two components, you are not supposed to include Fg. Okay, if you were to draw it this way, although it's not something that I really advise you to do. Okay, the weight, remember we're not including the weight now. So now we are going to have the normal force, the frictional force up the slope, and we are now going to have Fg parallel and Fg and FG perpendicular. This is what the free body diagram would look like if we used the two components, that is your FG parallel and FG perpendicular, instead of FG. But because this is a 3 marks question, it's unnecessary for you to draw both of them. And remember, we draw this particular one for the purpose of calculations. It's not the free body diagram that they are actually asking for. This is the one that we use for the purpose of calculation, so that we can see the forces that we're calculating. All right. Now, I hope that you are empowered, and this has been Butu Academy, lessons that empower. Please make sure that you practice as much as possible, especially this part of the lesson where you have objects on an incline, the drawing of the free body diagram together with the calculation of the components of the weight. It's quite tricky sometimes, especially when there are too many forces acting on the object. You get confused sometimes, but the more you practice, the better you'll become at dealing with situations like that. Once again, I hope that you are empowered. This has been Butu Academy, lessons that empower. We meet again in the next lesson, where we now start with the laws. We are going to start with Newton's first law, and we're going to break it down to what it means and how you apply it when it comes to calculations. Okay, we meet again on lesson 4. We're going to be looking at Newton's first law.